Thanks for the introduction. Today I'm here to talk about a second-generation compromised credential checking service. The number of password breaches have increased over the years. Billions of passwords are leaked every year. According to a recent report, in the first half of 2021 alone, about 5.4 billion records were exposed. With the increase in the number of websites and internet users, password breaches will become more prevalent in coming years. So I'll start by giving an overview of the entire credential ecosystem. So let's say there's a user, Mark, who uses his password to log into website A. Mark uses the same password for login purposes in website B. This is a very common, as prior work reports that 40% of users reuse their password across websites. Mark has also chosen a very similar password in website C by replacing the last digit 1 to suffix 123. So let us assume website A gets compromised, and the breach data from website A is compiled and sold over internet. This is very common, as attackers often use these breach compiled dataset to compromise accounts in other websites. In this case, attacker uses Mark's breach data to get access to his account in website B. This kind of an attack is known as credential stuffing attack and is likely the most prevalent form of account compromise today. So nowadays, websites often integrate with compromised credential checking services or C3 service to get latest breach notifications and prevent credential stuffing attack. Several companies like Google, Apple, Microsoft have deployed their own credential checking service. Today, checking for compromised credential is part of all major browsers and phone interfaces. So this stops credential stuffing attack. However, attacker can still generate similar variants of the breach password to compromise Mark's account in website C. This attack is known as credential tweaking attack. And prior work has showed using simulations that credential tweaking attack can compromise 16% of accounts in less than 1,000 guesses given access to one of the breach passwords. So to prevent this attack, in this paper, we designed a second generation of compromised credential checking service, I Get Pwned or MIGP. MIGP prevents both credential stuffing and credential tweaking attack. So we define a new type of compromised credential checking service called similarity-aware C3 service. We formalize similarity-aware C3 service setting and design the system MIGP. In this work, we also empirically evaluate the effectiveness of different similarity measures. We analyzed empirically and theoretically the threat of a malicious client trying to extract sensitive breach data, which we call as breach extraction attack, and propose ways to mitigate it. Finally, we report on an initial prototype of MIGP and show its practicality by deploying it at Cloudflare. To provide a background, currently deployed first-generation C3 service allows users to find out if their credentials are breached without revealing it to the C3 server. Some of the properties of the protocol is that it protects client's password in the presence of a malicious server. Malicious client only finds out if their credential is breached or not and nothing else, and the protocols are fast for large-scale deployment. So in this work, we introduce an updated version of compromised credential checking service, I Get Pwned or MIGP. This MIGP prevents both credential tweaking and stuffing attack. MIGP provides an interface where client can securely query their username and password. In case the credential exactly matches, MIGP returns a match, and in case the credential is similar to any of the breached entries, it returns similar. To realize such a system, we first need to answer these questions. Firstly, what is the security risk involved in deploying similarity-aware C3 service? The next question is, how can we define this? How can we define similarity? And finally, how can we implement a privacy-preserving deployable protocol that achieves this functionality? So to answer the first question, the security requirements of MIGP is same as that of a C3S system. However, we need to additionally answer this question of can a malicious client abuse the similarity checking feature to extract sensitive breach data from MIGP, which we call breach extraction attack. In other words, does this extra information regarding similarity makes the attacks more effective? We perform a thorough analysis of these attacks, and we show that the breach extraction attack in MIGP is less than currently deployed C3 service. We also propose various ways to mitigate it, and you can refer to the paper for more details. So given we have techniques to reduce breach extraction attack, we will now focus on the design and implementation of MIGP. So the next question is, how do we define similarity? Ideally, we want our similarity measure to help warn users if their password is vulnerable to online credential tweaking attack. Therefore, a good similarity measure is to call password W dash similar to W if W dash appears early in the guest list of a credential tweaking attack based on W. In other words, password W and W dash are similar if W dash is within top similar variants of W. So the next question is, what is the most effective way to generate these variants? State-of-the-art credential tweaking attack is computationally expensive, and therefore in our work we show that empirically derived weighted edit distance-based mangling rules works best both in terms of performance and efficacy. So now we will look into how we can integrate this similar variant checking into a protocol. The first way to extend our original C3 protocol is to generate n variants server side and add them to the database. We can then update the protocol to reveal upon a match whether the match was with the original breach password or the generated similar variants. However, this approach leads to increase in this storage and the bandwidth cost as the size of the bucket increases with the addition of the variants. The second scenario is when the variants are generated on the client side. So the user runs a protocol on the user variant and the M generated similar variants. Sorry, on the user credential and the M generated similar variants. The limitation with this approach is that leads to increase in the breach extraction attacks efficacy and client computation cost. Finally, we can take a hybrid approach where the client, we generate M variants client side and N variants on the server side. So we empirically explore different trade-offs in performance and security for client side, server side, and hybrid generation of variants to help practitioners decide which approach to choose. We use a 1.4 billion compiled breached credential dataset for simulations. So we take this dataset and divide it into two parts. The leak dataset is available to the attacker and the MIGP server, and the test dataset is used to sample target passwords for security simulation. For security evaluation, we record the efficacy of a credential tweaking attacker with 1,000 guesses in the presence of MIGP. For performance evaluation, we measure average bandwidth and client computation cost. So in this graph, we compare the different MIGP architecture. The exact checking corresponds to the currently deployed C3 service, which gives best performance best numbers in terms of performance. For client computation cost, MIGP server performs better than MIGP client. And in terms of storage requirement, MIGP client is better than MIGP server. MIGP hybrid gives a good balance between MIGP client and MIGP server in terms of client computation and storage respectively. If we look at the credential tweaking attacker's accuracy, the exact checking systems or the currently deployed C3 services are the most vulnerable to credential tweaking attacker. The attack accuracy for MIGP client and MIGP server is same, given both of them checks against the same number of variants. And MIGP hybrid is most robust against these attacks. Finally, all of this helped educate our deployment of MIGP in collaboration with Cloudflare, a major CDN and security service provider. MIGP is currently deployed as a public-facing API where users can query their credential, and is also a part of the new breach alerting feature within Cloudflare's web application firewall. To measure the effectiveness of MIGP, we instrumented a measurement study on Cloudflare's WAF deployment, and we concluded that MIGP is able to flag 20% more vulnerable login attempts compared to exact checking C3 service. With the large-scale deployment of MIGP and Cloudflare, we demonstrate the feasibility, practicality, and usefulness of checking for similar breach credential in a privacy-preserving way. Thank you, and happy to take any questions.